This is O-Levels Physics 5054, October, November 2025. These are the grade thresholds. I'm going to start with question number 1. It's a speed time graph, so the gradient, a preemptive assumption, moving on to the question, will be representing acceleration. Let's move on. He says, determine the speed of the car at time t equals to 0. That's going to be read directly from the graph. Do we know what this value is? This is 29. That's what I've written already. So distance traveled by the car between driver seeing the obstruction at t equals to 5.7 and the car beginning to slow down. So we're going to look for a time that is around here, because this is 5. So this will be 5.2, 5.4, 5.6, and 5.7, somewhere around here. From this point to 6 seconds, or 6.4. Yeah, 6.4. So he sees the obstruction at this location, but starts applying the brakes at this location. So this time frame will actually be utilized for the thinking distance, right? So it will be simply area under the graph in this section, roughly from this to this, all connected like this. So this is going to be 29 multiplied by 6.4 minus 5.7. This will be 20.3, which up to two significant figures is 20. The distance traveled with the car between t0 to t11.2. So it's asking me about the whole distance covered by the object between this time frame from t0 to 11.2, approximately here. So we can use the formula that is for parallelogram. That is, these are the two parallel sides, and this will be the height of that area. So this will be 1 over 2. Sum of parallel sides, which will be 6.4 plus 11.2 multiplied by the height, which is 29. And if you solve this, you get 255.2 meters, which up to two significant figures is mentioned here as 260. He says, state one factor that affects only the braking distance. When the car is being slowed down, the brakes have been applied. So mass of the vehicle, tire conditions, road conditions, brake conditions, and every condition that you've mentioned will have its own reason. So if you mentioned mass, heavier loads has more inertia, so more force is needed to stop, which is going to increase the braking distance. Tire conditions, if they are worn out, the friction is less, braking distance increases because there's less grip. If you're talking about the brake condition, same answer as worn out tires. The brakes, older brakes or poor braking performance leads to less friction, leading to longer braking distances. Question number 2. You might have noticed that this question is very similar and very common these days in the recent past paper. They ask you to talk about it in terms of forces applied or forces involved. So the motion of the container through the water until it reaches terminal velocity. So initially, the only force on the vehicle, on the object, is actually the weight. And the other one will be drag or viscous drag in some cases. You can use both words, it's fine. So we talk about from the very beginning. Initially, the weight causes the ball to accelerate downwards because there is no movement. It's very early. And as the object starts moving down, it gains speed. And as the speed increases, the drag also increases because speed is proportional to drag. Same thing when you run, you feel all the air gushing through you. If you're just walking, you don't feel that much of air. So because of this, the resultant force decreases, because the resultant force in this case will be F equals to ma. F is weight minus drag equals to ma. The weight is not changing because that's mg. The drag is increasing with the passage of time. So if you take away, for example, a larger and larger number, you subtract from weight, you are left with a smaller number of the resultant force. Since the mass is not changing, definitely the acceleration must be. And that's the full summary of the whole question. So if the resultant force decreases, leading to a smaller acceleration, and this only happens when the weight becomes equal to the drag. And eventually when they do, the resultant force becomes 0, acceleration becomes 0. When the acceleration is 0, we will say that the object is now falling at terminal velocity. It can't get any faster than this because there is no resultant force available. The next question is, the container falls through a vertical height of 32 meters before it hits the bottom. Calculate the energy transferred from gravitational potential energy. So what I would suggest is you simply write down the formula for the examiner. Gravitational potential energy equals mgh. Mass is 74. The g is 9.8. The h is 32 meters. The final answer will be 23,206 joules, which up to two significant figures will be written down like this in standard form. State the principle of conservation of energy. I would like to remind you that there's a new word from the syllabus or for the syllabus, and that is energy can neither be created nor can be destroyed. It scores you 1 mark, but it can change from one store, this is new, one store to another energy store. We used to call this form of energy, but now we will call this store of energy, and this is new vocabulary. So be careful about this. From today onwards, you will stop using the word form of energy. We will start using the word store of energy. And even in our explanation, we will be using that. Work is done to transfer energy, gravitational potential. Okay, fine. This question is repeated in terms of MCQs and P2 question. We've seen this here too. Describe in terms of work done how the energy transfer. Now, notice that after terminal velocity, there is no more transfer to kinetic energy. Why? Because terminal velocity means it cannot get any faster than that, which means even if you apply half mv square for kinetic energy's sake, the velocity is not changing. The answer of kinetic energy will not be changing. So even if the object still has some height to go, it's still above the surface of the Earth, still going down, the gravitational potential energy store still needs to get converted into something. It's converting into something else. In that moment, there is no conversion to kinetic energy, so there must be some conversion to thermal energy, which is responsible for heating up the object. And where does the thermal energy or this thermal energy actually comes from? This is actually categorized as work done against the drag forces, be that air resistance or be that viscous drag from a fluid. But that's what we're going to write down here. So there's no change in kinetic energy, hence now the gravitational potential energy is converting into the thermal store as work is being done to keep the object moving against the drag and viscous forces. So that's where the thermal energy store is being utilized or being stored as. Next question, question number 3, is an interesting question. That's a good question in terms of momentum. And this is a common example these days, water coming out of the pipe towards or directed towards the wall. What happens then? So in 1 second, this is important information, will serve us later. The volume of this water hits horizontally, the speed is 24, density is this, calculate the mass of water. So we're simply going to use the formula density is equal to mass by volume. Density is 1000. Mass we don't know. Volume is given to you over here, that this is what is coming out of the pipe. So mass is going to come out as 7.5 kilograms. Simply take this over there to multiply the horizontal momentum, which is simply going to be momentum equals to mass multiplied by velocity, which becomes 7.5 into its velocity while moving forward is 24. So that is going to be 24. This comes out as 180 Newton seconds, which is going to be written down here. Parts B, the horizontal momentum of the water decreases to 0. When none of the water bounces back from the wall. Explain in terms of momentum why the momentum calculated in A2 is equal in size of the force. Notice that this is actually a mathematical problem, okay? And that's what he's trying to explain in terms of a statement. So we understand that the resultant force or force is actually equal to change in momentum divided by time. The whole question revolves around the fact that everything is happening in 1 second. So if the object, for example, whatever that mass is, mv minus mu divided by t, this t is 1. So because this is 1, whatever the force is going to come out as is going to be equal to change in momentum. This is why when you calculate this, the change in momentum and the unit of force, which is going to be 180 newtons, is going to come out as equal because we're dividing with time t equals to 1. So this mathematics is being described over here. That force, or since force is the rate of change in momentum and time interval is equal to 1 second, force or calculating force yields the same answer as that of the change in momentum. And it's precisely because of the mathematics involved because of t equals to 1. Explain in terms of Newton's third law why there is a horizontal force exerted on the wall by the water. So we go this from reverse. First, we score the mark for stating Newton's third law by involving the objects that are present in the situation. So third law states that when water exerts a force on the wall also exerts an equal and opposite force on the wall. Since water has, you can ignore this statement. So since water has experienced a force that caused it to stop, because water is dropping dead at 0 meters per second, it must be true that the wall has also experienced the same amount of force. So it's more like saying if object A applied a force on B, then object B must have also applied an equal and opposite force on object A. So that's how we go about this question. Part D, he says, the pump that forces the water to refine. Explain why the force exerted by the water on the wall increased by a factor of 4. So you see he's talking about the force, and force is still momentum divided by time. Momentum is mass multiplied by velocity divided by time. What's actually happening is that they have increased the speed, has doubled. Now, we can very clearly see that the new speed will be 2v. But if the speed increases of the water, then for the same amount of time frame, which is 1 second, more amount of mass of water is also going to leave the hose. So mass will also be doubled, 2m, which is what leads to 4 times the mv, which is the original momentum. But that's what we explained in English. The momentum depends on the product of mass and velocity. As the speed doubles, the mass leaving the pole also doubles, leading to a net increase by a factor of 4. Question number 4, he says there is wax being melted over a period of 600 seconds. It's fine. Now notice the hint. The hint is how the figure shows this. How do you know that this is the melting point of wax is at 63? Because there is a horizontal line. That's what you see with your eyes over here. You see with this is horizontal. That's how you know this is the melting point. So that's exactly what you're going to write down, that horizontal line is observed, but where? At time or after time t equals to 400 seconds, meaning that the temperature is constant, indicating that this is the melting point of the wax. Now your answer is completed at this point, but adding this bit of information improves the quality of your answer. Part B1, he says, show your working and increase in the internal energy store. So it's very clearly a question of heat capacity, which is Q equals to mc delta T. The mass is given to us 0.04. Heat capacity is 2100 joules per kg degree centigrade, and we have to go from temperature time 0 to 220. So the delta T is going to be taken from the graph, which is at T0, the temperature is 21. At 220, roughly approximately here, the temperature is 48. Yeah, if you zoom in, you can count. So this will be 48 minus 21. This gives us 2268 joules of energy, which is 2300 up to 2 significant figures. Describe what you will see with your eyes. What happens to the motion of the molecules? What will happen to the movement of the molecules? What will you see? As the solid wax, as the internal energy of the wax increases. So when the internal energy increases, the thermal energy increases, the molecules gain kinetic energy and their speed increases. They start vibrating faster and more vigorously. This is from kinetic model of matter. The temperature of a system is proportional to the kinetic energy of the system molecules, which is then again proportional to the speed of molecules. Why do we land on speed? Because kinetic energy is half mv squared. We final conclusion is at speed. Why? Because it's actually the speed that's changing. And what's happening to mass? You see, if you're talking about oxygen, nitrogen, or carbon dioxide, any gas you're talking about. So when you use half mv squared, the mass m, if you're talking about oxygen, stays the same. So it's the velocity that actually represents the change in temperature. This is why we start with temperature, go to kinetic energy, and then land finally on speed. When the wax reaches its melting temperature, energy still continues to be transferred thermally to the wax. Describe again, explain what might be happening in terms of the forces between the particles. You see, if it is at melting point and still providing energy, the temperature is not changing, then something is off. That energy is going to be used to break the bonds or intermolecular forces. That's exactly what we've written down. So now, or from this point onwards, the energy supplied is given to the latent heat. This energy is utilized to overcome the forces between the molecules and break the bonds, or to set themselves free from that structure. So, and this is extra information. Your answer is complete at this point. This extra information improves the quality of the answer. When all the bonds are broken, a change of state has occurred or has taken place. Question 5 is from electromagnetic spectrum. Very rare to say a question like this one, but it is what it is. So I've mentioned all the spectrum, but we were only asked to mention M and UV. So this will be the microwave M, and this will be the UV region. The rest of them I mentioned for your memory, for your revision. The frequency is given to us, the speed is given to us, calculate the wavelength. Now, if you remember, the examiner used to miss out this information and students got puzzled and they couldn't solve this question. So what they've done is started giving you this information, but please be advised, if it is about microwave, radio waves, gamma, X-ray, anything from the electromagnetic spectrum, it is understood that they all move at the speed of light, which is 3 into 10 is about 8. So we're going to use the formula V equals to F lambda. And so this is 3 into 10 raised to the power 8. Replace all the values, which is 12. Now this is gigahertz, and 12 giga will be 10 raised to the power 9 into lambda. Lambda comes out as 0.025, which is written down here. Question number 2, describe how microwave is used. Now this is again an important question, repeated question. Please add these in your notes or memorize it. How satellites are used with the microwaves to transfer signals. So what happens is, if this is the Earth's surface, this is the satellite, this is one of the antennas, and this is the other antenna. This is the transmitter, this is the receiver. So this is where, for example, a TV channel might be being broadcasted, and this is where you're standing. You want to see that channel on your TV or, for example, on the internet. So signals are transferred to the satellite on the outside of the Earth, and those signals are amplified sometimes to send them back to the Earth to this spot. So that's how the signal is transmitted. And this is again caught by antennas over here. And that's exactly what we've written down here, that signals are transferred from Earth to satellite first using microwave. And the reason we're using microwave is because the layer of ionosphere or stratosphere, microwave lose the least amount of energy while being transferred from one atmosphere to the next one. So satellites transmit that data back to the Earth, where it is received by an antenna. Part C. All microwave ovens have a switch that turns off when the door is opened. Why a safety switch is there? You see, microwaves can cause tissue heating. If they were let out of the microwave environment, and if they reached you, they will cause burns, which is not a good condition. It's unsafe. So hence, a switch is needed to prevent the door from opening and causing harm to the person around it, right? So it needs to break the circuit so that the microwave does not keep running. An electric car is driven by direct current, and then he's asking us about the difference between DC and AC. It's a very simple answer. DC current flows only in one direction and is generally with batteries, capacitors, or batteries inside your laptops or mobile phones, or small ones that we use in our remote controllers or fire alarms. So while AC current flows in both directions in a complete circuit. The circuit is given to you, DC motor is given to you. It says in 120 seconds, the current of 41 passes from point P. Calculate the charge that flows through it. The actual equation is I equals Q divided by T. But in the syllabus, they've simplified this as Q equals to IT. We're going to use Q equals to IT. Current is 41 amps, time for 120 seconds. So how many packets actually got transferred? So this is actually 4920 coulombs of charge. 4920 packets of electrons have been transferred. Two significant figures goes 4.9 power 3. Part number 2, it says current is due to the electrons. Be advised, this electrons. Each electron carries a charge of this. Say the direction of the electrons, because generally we are thinking about the conventional current. The conventional current is going to be from positive to negative. But since he's asking about the electrons, it's opposite to the conventional current, which is from negative to positive. So at P point, it is going to the left. Or you can say it's going away from the motor. So there are two ways to describe what you are going to see. Away from the motor or leftwards. Now he's asking about the number of electrons. What we can do is very simple. You see, if one electron has 1.6 into 10 raised to the power minus 19 coulombs, then how many number of electrons will be in the previous number, which is 4920? 20 coulomb of charges. How many electrons will there be? So when you do cross multiplication, you get this answer of number of electrons to be the number of electrons you're going to get is going to be equal to 3.075 into 10 raised to the power 22. But this is in 120 seconds. He's asking us about 1 second. So we can divide this number with 120 seconds as given in the question, because this was total for 120 seconds. We want for 1 second. So the number of electrons to come out as 2.5625 into 10 raised to the power 20. You can do this directly as simply Q equals to I multiplied by T, which is 41 multiplied by 1, which is 41 coulomb of charge. Then place it here and do the same thing again, but in that step you won't have to divide this with 120. It's up to you what choice you take. The final answer will be the same. Part C. The power supply for the electric car is, okay, fine. Electromotive force is a part of the definition of the syllabus. Work done by the source in moving 1 unit charge around a complete circuit is its complete definition. So work done is a keyword and complete circuit is a keyword. Each cell contains 92 cells in series. Calculate the EM of the battery of one battery. So it's one cell is 3.7 volts. 92 are connected in series. So 3.7 multiplied by 92 gives me 340.4 volts, which will be 340. He said the power supply is made containing 85 of these batteries in parallel. Now in parallel, the voltage remains the same. So that's why it is 340 still. So what might the battery look like is 85 strands with approximately 92 cells in series, like this. These are 92 cells and these are 85 strands. So that's what the battery pack is going to look like. Question 7 is about the electric kettle. He says 2300 watts, 230 watts. The current a very common formula, I is going to be equal to 10 amps, very straightforward. He says the manufacturer of the kettle states that the kettle is safe for currents that are smaller than 15 amps. The wiring of the main supply on the wall is safe for the current smaller than 20 amps. Okay. Yeah, so this is the cable and the main power plug. So it says state the fuses available for the kettle that are rating are shown. We could choose 10 amp, but it will always or generally blow over because it's right on the edge. You see, the problem is we have to be slightly greater. But what if there's slight voltage fluctuation? So for example, this is 2300 watts. Current we don't know, but if the voltage drops to 210 volts due to some power consumption, due to line losses, whatever. So 2300 divided by 210 gives me 10.95 amps. So just a change of 20 volts from the main supply and the fuse that if we had selected 10 would have given off. It would have been blown over. So there's always a good idea. It's always a good idea to have a certain headroom. So it's always greater but closer. So it's going to be the 13 amp fuse. That's going to be the best option in this case. And that's how we describe the same situation, that it does not affect the normal operating current of the kettle, but still has some headroom to compensate for voltage fluctuations or any other leakage currents in that situation, in that case. But anyways, that's the answer for this question. We don't go for 15 or 18 because if they are too large, if you choose a too large fuse, it may take too long to respond, and by the time wires may have melted. Next, he says state the name of the wire the fuse is connected into. Explain why the fuse is connected to this wire. So all the safety equipment are always connected in live wire. That is something that we understand already. So be that a switch, be that a fuse, it has to be in the live wire. So the name of the wire is live wire, and explanation is if the fuse blows, it ensures that the connection from the live wire is disconnected completely. You see, the circuit is going to look like this. This is live wire, this is neutral, this is a switch, this is a fuse, this is your appliance, be that a bulb, a heater, or whatever. If the fuse gives away, for example, due to short circuit, if the fuse is melted, then successfully what you've done is stayed away from the live wire, which actually carries 220 volts or 230 volts based on the manufacturer and your location from the transformer. Right? So it's a good idea to be isolated from the live wire rather than being still connected to it. And that's why the fuse is connected in the live wire. The insulation of the live wire is damaged and it is exposed. Explain what happens when exposed live wire touches the metal outer casing. So if the metal outer casing is earthed, then all the current is going to go through earth. It's going to create a short circuit condition and the fuse will go away. It will melt. So a large current causes short circuit flows or short circuit to flow, which eventually melts the fuse, protecting the circuit by breaking it completely. Part C, household bill, very easy. The kettle is switched on for 34 hours. Calculate the energy bill. So it's 2300 divided by 1000 because we want to convert this into kilowatts, and hours is hours. So 34, and this will be, since this part is the kilowatt hours, the energy consumption, multiplied by the cost per unit kilowatt hours. This is 0.32. So this is going to come out as $25.02. Question 8, state one way in which the composition of atoms of lithium isotopes are same. So sometimes he's asked about the difference. Today he's asking about why they are same. They have same number of protons and electrons are the same, but the neutrons are different, which is going to be part of the next answer. State one way in which the composition of lithium atom of one isotope is different from the composition of lithium of different isotope. So they all have same protons and electrons if they're neutral, but the number of neutrons will be different. Part B. There are 3 electrons in the orbit of the nucleus, so we understand that these dots represent the electrons. And determine for X and Y, you see the lithium composition. Yeah, if this is a neutral atom, you see we have 3 electrons, and we have 3 members that are transparent and 2 members that are slightly grayed out. It's quite possible that these are the protons and these are the neutrons. If I were to write down a representation for lithium, which is protons plus neutrons, and this is protons, so it should have 3 on the base, and protons plus neutrons, which is 3, and these are 2, so this will be 5. The representation should look like this, which is what I've done here. An ion of lithium isotope has a charge represented as this, so 1 electron is gone. Describe how the diagram that represents this is changed now. We have to refer to this diagram, so we're going to talk about that 1 black dot in the shell is missing. There is 1 less electron here or somewhere else. Or you could have said that only 2 black dots visibly drawn representing the electrons in the shell. So something that you describe that you're going to see with your own eyes. Part C. State 1 damaging effect of nuclear radiation, cell death, cancer cell mutation. Very basic answer, straightforward. This is also a good question in terms of being repeated. I would advise you to remember its marking scheme and write this down in your books somewhere as notes. So randomness is unpredictability in terms of direction, time, emission, does not follow any pattern. We don't know what's going to happen next. And let me give you an idea. So for example, if there are 1,100 atoms in a sample of radioactive element, can you pinpoint exactly which one of them is going to decay next? You cannot do that. And when it does decay, for example, can you predict the direction of the daughter particles? You cannot do that. And what is going to happen next is again unpredictable. So that's why we call this behavior as random. And there is another point for this. It actually shows fluctuations on the GM tube graph that we sometimes draw like this. The graph has fluctuations, and this also contributes to the random nature of radioactive emission. Spontaneous is that the emission does not need a trigger. It's going to happen on its own without the intervention or requirement of chemicals, acid, bases, pressure, high temperature, or anything of that sort. That generally works in chemistry. It generally increases the rate of chemical reaction in chemistry, but in physics, nuclear reaction, doing these things which we generally would do to check a change in reaction, they do not affect nuclear reactions. So that's why we categorize this behavior as spontaneous. It's happening on its own. Space physics. All right, he says that the sun is 26,000 light years from the center of the Milky Way galaxies. Speed of light in vacuum is this kilometers per year. Determine the distance from the sun to the center of the Milky Way. So simply, if we have these many light years available, in 1 year, if it covers this much distance in kilometers, we can simply multiply these two numbers together. So 9.5 into 10 to the power 12 into 26,000 years of availability to keep moving. This comes down to 2.47 into 10 to the power 17, which becomes 2.5 power 17 to 2 significant figures. The sun takes 2.3 years to orbit the Milky Way. Calculate the speed v, which is going to be simply v equals orbital speed 2 pi r divided by t equals to 2 pi into 2.5 into 10 to the power 17. Now notice that this is kilometers and this is meters. So we have to be careful. So adding another 10 to the power 3 member to convert this from kilometers to meters divided by the time for these. This is in years. So this will be 2.3 into 10 to the power 8 into 365 into 24 into 60 into 60. This is going to come out as 2.17 into 10 to the power 5 meters per second, which is two significant figures written down over here. Part B1. Near the end of its life, a massive star becomes a red supergiant. Describe what happens inside the star as it becomes a red supergiant. So most of the hydrogen at the center gets converted into helium. Outward region expands due to radiation pressure, and the core keeps contracting more and more so that the remaining hydrogen fuses to become more elements. Describe how a red giant produces a black hole. So a red supergiant explodes into a supernova, producing a nebula, leaving behind a black hole. These are all memory-based questions. I can't really help you with them. You have to memorize the whole process or the tree of the star formation. This is an important question, repeated part. He says, describe how heavier elements are produced. During the explosion, supernova explosion, lighter elements, due to the immense pressure and temperature, again fuse together to make heavier elements. So just imagine that the whole universe started from helium, sorry, not helium, but hydrogen. Hydrogen decided to fuse together to helium. And during these stages of the life of a star, helium keeps fusing together to make iron, to make uranium, to make polonium, to make plutonium. So all the elements of the periodic table have existed somehow at the center of a star. This is why sometimes, in English expression, we sometimes say that human beings are made out of stardust. I will see you in the next paper.